Today, we're going to be tackling something pretty fascinating.
Yeah, definitely.
You sent this research paper over, and it got me thinking about, like, the power of small things. We're
Absolutely.
talking, like, incredibly tiny particles that can totally change how we think about heat. Like, seriously tiny.
Yeah, nanoparticles. It's pretty amazing what they can do.
Nanoparticles, yeah. So we're diving into a paper called, and this is a bit of a mouthful, Boundary Layer Flow of a Nanofluid Past a Stretching Sheet,
hmm
from the International Journal of Heat and Mass Transfer, all the way back in 2010.
One of the early ones for sure,
Yeah.
but still super relevant, even now.
Yeah,
Yeah.
exactly. I mean, this is like the foundation for a lot of the stuff we're seeing today, right?
Totally. It's like the building blocks.
So, okay, why should we care about this? We're talking about, like, making heat transfer better.
Yeah, and not just in some obscure lab setting. This has real-world implications.
Yeah. Big time. Think about it, like everything from how we cool our electronics to how we make plastics.
Even to, like, potentially large-scale energy systems.
Yeah.
It's pretty broad.
Right? I mean, that's huge, right? If we can make heat transfer more efficient, it changes the game.
It's all about efficiency, yeah. Less energy wasted, better performance, the whole 9 yards.
So this paper, it's asking a pretty specific question.
Yeah, it's getting into the nitty-gritty.
It's like, okay, we've got these nanoparticles in a fluid, and then that fluid is flowing over something that's being stretched.
Right, a stretching sheet.
So, like, how does that stretching in the nanoparticles affect how heat and mass are transferred?
Yeah, they use some pretty hardcore math to figure that out.
Math, yeah. I'm more of a, like, big picture person, but the results are what's really cool.
Definitely. Let's break it down.
Okay, so first things first. What's the problem they're trying to solve?
Well, the thing is, a lot of the fluids we use for heat transfer, like water, oil, even antifreeze,
Everyday stuff.
they're not actually that great at it.
Oh, really?
Yeah, their thermal conductivity or how well they can conduct heat isn't ideal for a lot of applications.
So it's like they can move heat around, but not as efficiently as we'd like.
Exactly. They're kind of sluggish.
That's a problem.
Huge problem.
Yeah.
I mean, think about it. If your cooling system isn't efficient, you waste energy, things overheat, it can even be dangerous.
Makes sense. So what's the solution? These nanofluids, right?
Bingo. That's where the magic happens.
Okay, so nanofluids, what are they exactly?
So imagine your typical fluid, like water. Now, take some incredibly tiny particles, like on the scale of nanometers.
Nanometers, that's like incredibly small.
Unbelievably small. A billionth of a meter. You can't even see them with a normal microscope.
Wow.
You basically sprinkle those nanoparticles into your fluid, and boom, you've got a nanofluid.
So it's like a regular fluid, but with these tiny, superpowered particles added in.
Exactly. And what's crazy is that even adding a tiny amount, like less than 1% by volume, can make a huge difference.
No way. So like a little pinch of these things can supercharge the fluid.
That's the idea. It's like adding a secret ingredient that boosts its heat transfer abilities.
And you said this guy, Choi, he was one of the first to really look into this.
Yeah, Stephen Choi. Back in the mid-90s, he was doing some groundbreaking work, showed that you could potentially double the thermal conductivity.
Double it? That's insane.
Yeah, the potential is huge.
Yeah.
Because these nanoparticles, they have such a large surface area compared to their volume.
I see. So they're tiny, but they have a lot of surface area for heat to interact with.
Right, and they're often made of materials that are really good at conducting heat themselves.
So they're like little heat transfer machines zipping around in the fluid.
Exactly. They boost the fluid's ability to move heat around at a microscopic level.
Okay, so that's the nanofluid part. Now, the stretching sheet thing, why is that important?
Well, think about how a lot of materials are made, like polymer sheets, filaments, even metal wires. They're often produced by stretching.
Right, like pulling and thinning them out.
Yeah, and as they're stretched, they're also cooled down. And how that cooling happens, how heat is transferred away, that's crucial.
It makes sense. So the way the fluid flows over that stretching surface is going to affect how well it cools, right?
Absolutely. And that's where this research comes in. They wanted to understand how a nanofluid behaves in this specific scenario.
Because it's different from just like a fluid flowing through a pipe or something.
Totally different. The stretching adds a whole new layer of complexity.
And this builds on earlier work by, was it Crane?
Yeah, L.J. Crane.
Yeah.
He did a lot of work on the fluid dynamics of stretching sheets, but with regular fluids.
So this study is taking that and saying, okay, what happens when we add nanoparticles to the mix?
Exactly. It's like the next level.
Okay, so they set up this experiment. Now, the paper starts talking about these dimensionless numbers.
Ah, yes. The world of dimensionless numbers.
I gotta be honest, those always kind of make my head spin a little. Can you break those down for us?
Absolutely. So these numbers, they're basically ratios. They compare different properties of the fluid and the flow.
Okay, so it's not like a specific measurement, but more like a relationship between different things.
Exactly. And the cool thing is, they don't have units. So you can use them to compare different systems, regardless of the size or the specific fluid.
That's pretty neat. It makes it more universal, right?
Exactly. So in this study, there are 4 main dimensionless numbers they focused on.
4. Okay, let's hear about them.
All right. First up, we've got the Prandtl number.
Prandtl, okay. What's that one tell us?
It's all about momentum versus heat. Basically, how easily momentum spreads through the fluid compared to heat.
Momentum, like the fluid's movement.
Right, so like if the fluid is thick and sticky, momentum spreads slowly.
Okay. And heat would be how fast the temperature evens out, right?
Exactly. So a high Prandtl number means momentum is dominant.
Okay, I think I'm getting it. What's the next one?
Next up, we've got the Lewis number.
Lewis. All right. This one's about.
This one compares how fast heat spreads to how fast the nanoparticles spread. And the nanoparticle spreading, it's all about Brownian motion.
Brownian motion, like the random jiggling of particles?
That's it. So the Lewis number is basically saying, is heat spreading faster or slower than the random movement of the nanoparticles?
Interesting. So that one's really about the nanoparticles themselves.
Exactly. And that brings us to the next two, which are even more focused on the nanoparticles.
Okay, I'm ready. Hit me with them.
All right, we've got the Brownian motion number.
So this one's all about that random jiggling.
Exactly. It tells us how strong that Brownian motion is and how much it affects the heat and mass transfer.
So like if it's high, the particles are really bouncing around, and that's going to impact how things move in the fluid.
Right on. And then finally, we've got the thermophoresis number.
Thermophoresis, that sounds intense.
It's a cool phenomenon. Basically, it means particles move from hotter areas to colder areas.
Oh, so they're like seeking out the cold?
In a way, yeah. And the thermophoresis number tells us how strong that effect is.
So it's another factor that's going to influence how those nanoparticles move around.
Exactly. And all 4 of these numbers, they play a role in determining how this nanofluid behaves on that stretching sheet.
Okay, so we've got our 4 key players: Prandtl, Lewis, Brownian motion, and thermophoresis. What did they find out?
Okay, buckle up. Here comes the good stuff.
I'm ready.
They measured something called the reduced Nusselt number.
Nusselt number, that's about.
It basically tells us how well heat is being transferred from the stretching surface to the nanofluid.
Okay, so it's like a measure of how efficient the heat transfer is.
Exactly. And here's the kicker. They found that as the Brownian motion number and the thermophoresis number increased, the Nusselt number went down.
Wait, so more movement of the nanoparticles actually led to worse heat transfer? That's counterintuitive, right?
It is a bit surprising. You'd think more movement would mean better mixing, better heat transfer, right?
Right, like if they're bouncing around more, they'd spread the heat more effectively.
But it seems like, in some cases, it can actually have the opposite effect.
How come?
Well, think about it. If the nanoparticles are all clustering near the hot surface because of thermophoresis, they might actually create a kind of insulating layer.
Ah, so they're blocking the heat from getting to the rest of the fluid.
Exactly. Or if they're just bouncing around randomly, they might not be moving in a direction that actually helps transfer the heat.
So it's like they're moving, but not in a useful way.
Right. They're not actually carrying the heat away from the surface efficiently.
And the paper shows this in those tables and figures, right?
Yep. They got some really clear visuals that show this trend. It's pretty fascinating to see.
Okay, so that's heat transfer. What about mass transfer? Like how the nanoparticles themselves are moving within the fluid?
Good question. They measured that using the reduced Sherwood number.
Sherwood number. And that's similar to the Nusselt number, but for mass instead of heat.
Exactly. And here they found something interesting. As the Prandtl number and the Lewis number increased, the Sherwood number went up.
So in this case, higher numbers mean better mass transfer.
Right. It suggests that if momentum and heat are spreading effectively, that also helps the nanoparticles to disperse.
Okay. What about the Brownian motion and thermophoresis numbers? How did those affect mass transfer?
It's a bit more complicated. It seems like sometimes they help, sometimes they hurt, depending on the values of the other numbers.
So it's not a simple relationship. The movement of the nanoparticles can either help them spread out or cause them to clump together, and it depends on the other conditions in the system.
Exactly. It's a delicate balance.
Okay, so this is all super interesting, but what does it actually mean for like real-world applications?
Well, think about it. If you're designing a cooling system, for example, you want to get rid of heat as efficiently as possible.
Right, like in a computer or a phone.
Exactly. So understanding these dimensionless numbers can help you choose the right type of nanofluid.
So you could pick nanoparticles that will move in a way that maximizes heat transfer.
Exactly.
Hmm.
Or, in some cases, you might want to control the movement to prevent that insulating layer from forming.
Ah, I see. So it's not just about adding nanoparticles, it's about understanding how they'll behave in your specific system.
Right. It's about fine-tuning the recipe.
And this applies to other processes too, right? Like that stretching sheet thing?
Absolutely. If
Yeah.
you're making polymers or metals, knowing how the nanofluid interacts with the stretching process can help you optimize the cooling.
So this research is basically giving engineers a toolbox to design more efficient systems.
That's the goal.
Yeah.
And it all comes down to understanding those fundamental principles, those dimensionless numbers.
Okay, so this paper was from 2010. What have we learned since then? Where do things go from here?
Well, the field of nanofluids has exploded since then. There's so much research happening all the time.
That's exciting.
Yeah, and this paper, it really laid the groundwork. They identified those key parameters, those dimensionless numbers.
Right, so now researchers can build on that and explore even more possibilities.
Exactly. They're looking at different types of nanoparticles, different base fluids, different applications.
Like a whole new world of possibilities.
Totally. And it all started with this kind of fundamental research.
So let's wrap things up for our listeners. What are the big takeaways here?
I think the main message is that nanofluids have huge potential. They can really change the game when it comes to heat transfer.
Right, but it's not as simple as just adding nanoparticles and calling it a day.
Exactly. It's about understanding the complex interactions, the role of those dimensionless numbers.
And how those tiny particles can have a big impact on the overall behavior of the fluid.
It's a really fascinating area.
It is, and it makes you think, what else could we do with these nanofluids?
That's the big question, right? What are the next frontiers?
Exactly. So here's something for you to ponder. We've talked about heat transfer, but what about other applications?
Oh, yeah, there are so many possibilities.
Like, could we use nanofluids to improve chemical reactions or to deliver drugs more effectively in the body?
I mean, people are looking into that, and it's super promising.
Or even for environmental cleanup? Like, could we use them to remove pollutants?
It's all on the table. It's a really exciting time to be following this field.
It is, and it all goes back to that idea, the power of small things.
Absolutely. Sometimes the smallest changes can have the biggest impact.
So thank you for sending us down this rabbit hole. It's been a wild ride.
Anytime. Always happy to dive deep.
And to our listeners, keep those curious minds engaged. Who knows what amazing discoveries are waiting out there?
There's a whole world of knowledge to explore.
Until next time, keep learning, keep exploring.
And keep those questions coming.
We'll be here ready to dive in.
Absolutely. See you in the next deep dive.